Thank you very much, and thank you for the introduction. Thank you also for the opportunity today to present you a bit of work and advertising GPR also for the agricultural sense. So I'm very happy to be here today. So I thought today a bit about, okay, what do I bring you? Because I think probably some of you have used geophysics already somewhere in the field, but most likely hardly any GPR was used. So therefore I thought I'd give you some ideas about how can we do it, how we improved in the last years, and maybe also to give you some ideas how you could maybe apply it as well to your applications. So of course, I want to acknowledge a lot of people here that were involving in all of these works. And this work was, of course, mainly funded FINOROP, but also with the soil radar system and also soil free. So just, yeah, okay, no, it doesn't work. Let's do this way. Okay, so I think most of you are pretty much aware of the system that we are looking at. So when we want to characterize the soil plant continuum, we need to think about a lot of different aspects. So starting from the plant, from precipitation, evapotranspiration, transpiration processes, but also from the capillary rise from groundwater. So a lot of processes are taking place in the subsoil. That also when we want to investigate the effect of the roots and the related soil properties that we need to account for. When we look a bit in the field of geophysical methods, we have some possibilities that we can apply in the sense of agrogeophysics. And each of these methods provides us a different physical quantity. And something that you should keep in mind when we talk about geophysical methods and the information that we would like to retrieve, we need a physical contrast. Otherwise, we're not able to see anything. So if there's an entire homogeneous soil, we hardly will get any information. But we need contrast. And these contrasts we can interpret. So either we can look at structural changes in the subsurface, or we can also look at, for example, fluid dynamics if we look at changes over time with time-lapse data. But one problem that we also have is that our physical properties needs to be translated into a property that, for example, in agriculture or hydrogeology can be used. So for example, water content, porosity, ion concentrations, or even like hydraulic conductivity. So there we always need to find a link. So this is also one of the problems that most of the methods do have in geophysics. So when we look, for example, around to like electrical resistivity measurements or EMI measurements, they all give us electrical conductivity, which is quite nice and very sensitive to many of different aspects, but it's also affected by, for example, temperature. So therefore, many things come together, and then to entangle this again and to really see the effects of the soil root systems is very tricky. And this is exactly where GPR comes in, because it provides us the electrical conductivity, but also permittivity. And the nice thing is with permittivity, it has a direct link to water content with petrophysical or complex mixing models. So we have a direct relation to water content, but we can also have investigations of electrical conductivity that again gives us information about ion concentrations. So we have technically one method that is sensitive to different soil properties at the same time. Plus, when we also look a bit in the range of the frequencies that the methods are using, so this is like just the domain of here frequencies that electromagnetic methods have. The GPR method is actually the method that uses the highest frequencies, meaning it has the shortest wavelength and can therefore obtain the highest resolution images in the subsurface for field methods. So again, here we have then here also a nice opportunity to get high resolution images. So by keeping this in mind, we actually have a pretty nice tool here that can give us a good investigation of the soil plant continuum. We also have some drawbacks. We need to keep this in mind as well. So for example, in very clay-rich environments, our electromagnetic wave is very much attenuated and we can't see things anymore. So therefore, we are not suitable to be applied. And therefore, then electromagnetic induction, for example, works better. So it's always good to have complementary methods applied in the field. So in one case, one is not working, the other works most of the time quite nicely. But let's assume that now we have environments where GPR works okay-ish. So I thought about what to bring you. So I decided to show you some case studies that we did close by to the Forschungszentrum in Jülich at our Sellhausen test site. So we have some test sites that are all connected to Jülich, and especially in Sellhausen, we have done many investigations in terms of geophysical characterization of the subsoil. So just some images here, what we all have there. And then we also have here a closer look at the map. we have here a bit color-coded some electromagnetic induction data, which gives us electric conductivity and already gives us information about structures. So we know that we have an upper terrace and a lower terrace here at the Sellhausen site. And you already see here with the images, with the colors, that there are domains with a higher value and some with a lower value. And these values are related to electric conductivity. And our so-called bare field, where we have done these investigations and where also the rhizotron facilities are located, have both of these soil characteristics included. When we then, and that's why I thought it's quite nice to look here at 3 case studies. So one that uses the multi-channel GPR to look at structural changes and water content changes at our bare field site. The second study is then looking into how can we use geophysical data to look into fertilizer changes. And then the third one is the rhizotron data that basically combines all of these aspects together, where we really want to see how can we entangle the signals related to the soil plant continuum. Just keep in mind when we just have these both soil types here, so the one with the greenish part has a lower electric conductivity, meaning it's quite good for GPR in the end, and is related to a gravelly loam with a lot of stone and with a lot of soil heterogeneities inside. And the reddish part has a bit higher electric conductivity, so not that great for GPR in the end. And we have here a silty gravel. And also in terms of porosity, they're quite different. While we have on the lower terrace porosities around 23, 25%. On the lower side, we go up to 40-ish around. So we already have here really different soil types that we can investigate. So coming to the multi-channel. So why do I want to show you this here is basically because it has so much benefits in contrast to standard GPR methods in the end. And this is what I would like to show you today. So here you can see a typical single channel GPR device that is also often around. If you do other applications, this is what you can mostly find in the field, where you basically have here one transmitting antenna that emits our electromagnetic wave. And then we have here a receiving antenna that is recording the changes that the wave is happening in the subsoil at the other location. And what you normally have is that you put them in a sled and you just walk along a profile and keep the constant spacing of transmitter and receiver. So this is very fast and gives you pretty good information about structural changes. But the problem that we have with this method is that we do not get really a velocity information. So we can measure our waves when they arrive, we can see the time when they arrive, but to get the velocity and also then the depth of structures, there needs to be a bit more behind. So we need other methods to do this in the end, or we just assume something. So one option is to improve this is to do point measurements, where we have one transmitter antenna and a receiver antenna, but then we change the location of the receiver. And while we have the multiple informations and more rays, we can get an information about depth and velocity. And such measurements can then be used to correct such profiling data, for example. But the problem is that these point measurements take quite a long time, so kind of 10 to 15 minutes per one location, where you then have higher resolution images in the end, or more information about the structures. And that's the nice thing that the multi-channel device is basically combining, because in the end you have here one transmitting antenna and multiple receivers. So you have a lot of profiling information, but also at each location that you measure one of these point measurements. So therefore, you can have along your profile very detailed depth and velocity information of your soil that you can then relate to water content in the end. To just show you this a bit more in detail, so it's, as I mentioned, we have one transmitter, multiple receivers. In this case, it's a 500 megahertz antenna. It's a kind of intermediate in frequency, and it doesn't penetrate that deep into soil, maybe maximum in a nice soil, maybe 1.5 to 2 meters, I would say, but it's quite nice to look into the very shallow changes of the water content. And we do the measurements then every 2 centimeters, and this is, for example, how the data looks like. So we have here an air wave that we can nicely see, that is the wave traveling somewhere here, and then we have the so-called direct ground wave. And this direct ground wave can be used to estimate the water content at this specific location. And to prove you a bit the concept, and also there is some more behind, like also how the calibration of the system is done, but in the end it's quite easy to apply in the field. So coming to the site, so this is our bare field, as I told you already before. This is how it looks like from an image from on top. Here are the rhizotrons, here and there, and here also the lysometer facilities that we have. And the side that we measured is from kind of going up, down from here. So it's 120 meters. We see kind of roughly the distribution of the gravel and clay content. So here in the upper part, we have a higher gravel content that also goes along with lower lower electric conductivity that we know from the EMI data. And then we have an increase downwards the hill slope, where we also have a higher clay content. So that's pretty much what we know from the site already. So that's the profile line, and along this line we measured now with the multi-channel, but we also did some point measurements to validate the findings that we have with the multi-channel device. Something that you also need to keep in mind, this multi-channel device actually produces a lot of data. And it actually goes also along that it's hard to investigate each of the measurement points by hand because you get more than thousands of locations that you have them. So therefore, we also implemented some automatic routines. And to see if our automatic routines really give us reliable results, we double-check this with point measurements. So that's what you can see here. So at one location, this is one of the measurements that you can see here. Again, the air wave and the ground wave that can nicely be picked, some deeper reflections that are hardly visible. And the velocity of our ground wave here is approximately 0.06 meters per nanosecond. In terms of permittivity, that's actually a quite high one, so it's also from the water content not that low. So when we now go here and take the 7 traces out that are corresponding to our multi-channel device and compare to the multi-channel, just as a side note here, we get the same velocities. So it's actually first good thing, proof of concept, even with the limited data, we get the same results. So therefore, we can really apply it on the entire site. So that's what you can see here. So this is one of the data sets for one of the receiver combinations. So actually the one which is most furthest away, where you see here the air wave and here the ground wave. And you see some deeper reflections coming in here, but they are quite weak. Also here you see a bit more deeper down, and that again corresponds to the lower electrical conductivity domain in the upper part of the bare field. When we now see here, this is the, in the end, the velocity of the ground wave that is handpicked at every other location. And this is the automatic routine. They also go nicely along. And also when we compare this to the single channel data, they are in a good correspondence. So what we see is that the velocities along the profile change. We see definitely heterogeneities along the profile. We see here a domain where we have higher velocities. And here's a bit of weird spot that is, but that's actually related to some tractor lines. So it's always there where some of the big cars basically cross, and so therefore it's very much dense there. And we see here clearly these effects. So that's something related to the management in the end. And this we can nicely now apply to this profile and see changes also over time. So for example, when we had once done the profile in January, we see that the velocities are generally a bit lower than in November, which indicates also that there is a change in water content, so meaning the November was a bit drier. So in the end, what you can think about is that velocity is kind of reciprocal to permittivity, and permittivity goes in line with water content. So that's what you also see here. So this is like the time-lapse permittivity results here now, just color-coded along the profile. So blue is a low permittivity and it's related to a low water content, while high permittivity is related to a high water content. And you see here that in November, we have kind of intermediate results. In January, it gets way wetter, especially in the lower part, where we also have the higher porosities. And then we again in January and October, we have again a bit lower values. And when we then also look here at the transformed soil water content after Topps equation, which is an empirical relation, and the data is temperature corrected too, we can nicely now have here the water content along the profile in the end for these 4 different dates, and now see really the changes in structural terms of sense, but also in terms of water content variability along the site. So this gives us pretty good hope that also this multi-channel device is quite suitable to map water content changes at the field scale in a pretty fast and automatic manner meanwhile. We also compared, of course, our results to really double check if the results that we have are okay-ish. And in the end, it wasn't a good comparison also to, of course, the precipitation events were taking place, so they went in the same direction. And also we had some TDRs installed from another study that you see in some seconds, where we could do the comparison to, and they were also in a pretty good agreement, actually. So that really gives us confidence that this multi-channel device is suitable for soil water content mapping. Which brings me already to the second slide, because we now saw that, okay, we can do water content and structural changes, and this in a fast way. But another aspect that also in terms of agriculture management comes into place, of course, is fertilizers. Do we need more fertilizers in certain soil conditions or not? Where does the fertilizer go, and all of these things. And therefore, we also try to see, okay, what can we do with multiple geophysical methods, and how can we investigate your different fertilizers and the impact on the soil when no plants are on top. So we try to make it less complicated at this point. Again, we are here at our bare field, and for this study, we were first looking for a domain which is kind of not that heterogeneous. I don't want to say homogeneous, because there's definitely no homogeneous soil around, but we were looking for a spot here that has less heterogeneities. So when we look here at the EMI maps for different depth of investigations, we kind of said, okay, that's an okay spot that seemed kind of good to install such an experiment. And what we did was that we defined here certain patches with 3 by 3 meters and applied different dosages of fertilizers. So we had calcium ammonium nitrate and potassium chloride, and we had like in standard application, one with the double amount and one with the 10 times higher dosage than normal. And we had also some references. Then over more than 1 year, we did measurements with TDRs that were installed on the site, with the EMI, ERT, and GPR, and also additionally we did soil sampling. I do not have time to show you all the data here, but I just want to show you a bit the potential of each of the methods to see the changes over time. So let's get started with the EMI, because it's a tool that you can really nicely apply fast on a large scale, right? So when we look here at one of the very shallower depth of investigation coils, so it's a very shallow part of the soil now here, we see that over the time, so this is time over the measurement time application, and we see here a dramatic increase first of all of them electrical conductivity results, so especially for the ones with the 10 times higher dosage in the end, but also all of the others are also reacting. And then we see a drop, and then we see again a change. And this is exactly why it's so complicated with the electrical conductivity, because we also see an effect here of moisture, so of course from precipitation. When we look here at the day, what is it, 100-ish, so a bit before here, we have a pretty high rain event. So therefore this increase here is related to a changed water content. So to really see here the differences, what is related to what, you need also additional information, like really TDRs, soil water content measurements from some other information, but also here precipitation data. But we can definitely see also this two-folded applications and the other ones over time as well. But we need additional information. Looking at the ERT, so we had 5 ERT profiles, so it's the same profile, but 5 time steps. That we can also see here the changes over time. So here in the beginning, we see it's quite homogeneous, as we were hoping for from the EMI data. And we see especially from like the ones with C indicated, that's the one with the 10 times higher application. We see clearly here this increase in electrical conductivity with the red spots that are also changing over time, basically going downwards and also more spreading. But we see also with the double dosage here that are also here some nice little indicators for these parts as well, but also here not visible. So we can also use here the ERT to see the changes a bit more on a spatial scale. But for the ERT, it's the same with the with the EMI, it's the electrical conductivity. So we also see here effects of precipitation, and we need to temperature correct the data. But it can be used with additional information to also look here at changes of fertilizers. And then when we look at the GPR, so unfortunately we don't have that many data for GPR because it's not the best soil for GPR, and also before it's not maybe the best idea to look at changes in ion concentration, because ion concentrations is more attenuating our GPR waves. So it's actually not the first instrument you would think of as a geophysicist to be used. But still we did some GPR lines as well, and this is here from the beginning, so it's kind of not much happening here. And here we see some amplitude information in the end. And when we look here at one of the data that's at a later time, so it's 135 days after the application, we see clearly here at the locations with the very high dosage, there is a change in our signals. We see different phases and we see totally different amplitudes. So you can clearly see here this increase of the amplitude parts here and here as well, and no information from deeper down. For the other spots, it's very hard to see something. But still, this gave us a bit the hope that, okay, even with the GPR, we can maybe also see some indicators here for nitrate applications. So therefore, I didn't want to give up on this. And we also applied this now to some other tests and to also see how we can use really the information that is holding here and also the later arrivals and with the high peaks to also see changes, very small changes in the amplitude. And if we could maybe find a link also to nitrate as well with the GPR data. Which brings me then in the end to my last example, because there we basically combine everything. So the Resotron facilities, I bet most of you are aware of them, has the big advantage that we can not just control all the conditions that we have in terms of the environment, but we also can characterize the soil water content. We can look at changes over time. We can look at different changes at different plants and also different soil types. And also, we also started looking at changes in nitrate applications. So it's actually quite nice because we see all the controlling effects and we can monitor from different steps below in subsurface, but also have the proof from additional sensors and from the root information that is, of course, a direct link to the plant development. So looking here, just as a small wrap up here at our Resotron facilities. So this is the upper terrace, again, the one with the more stone content environment, and the lower terrace Resotron. Each of them is 10 by 7 meters, and we can enter into the below ground here with an access trench, and that's how it looks from the inside, where we have then the horizontal plastic tubes that we can access with the camera and the GPR systems. So there's also this nice data paper where we continuously add the data that we acquired since 2014, where we had wheat or maize. And the study that I'm going to show you here today is mainly concentrating on the maize, because it actually shows pretty nice patches and correlations to between GPR and root data. So just again, this is how it's set up. We have 3 different plots. So normally we have here either different management, like irrigation or sheltering, or we can have different kind of cultivars. And in this study that I'm showing you today, we just have different types of maize plants in the end. So we have here then our access tubes, as I mentioned before, where we can do the geophysical measurements. And what we do here is that we have one transmitter in one borehole and one receiver in the other borehole, and we just measure the direct wave in between. And since we know the distances between the tubes, we can correlate directly or can directly get the velocity of our electromagnetic wave and then calculate in the end permittivity and water content. It's quite straightforward, but in also monitoring purposes, we can't really measure more because acquiring the data takes even half a day for the GPR data and 1 day for the root measurements. So it's also something that we need to keep in mind in terms of measurement strategies and what we can do. Most of the studies we have done so far were using a 200 megahertz antenna, so kind of a wavelength of a meter. So the resolution is not that great, especially if you would technically want to investigate the soil root zone, which has, of course, very small features. But nevertheless, that was by that time the only commercially available system. And this is how the typical GPR data looks like. So we have here travel time, we have here distance along the tube, and this is just color-coded amplitudes. But you see nicely here different arrival times that we can pick and estimate the permittivity. And in the same tubes, we then also get the root images at some of the locations. So also it's just at some locations, really not the entire tube length. And at this time, we had a 2 by 2 centimeter images. And nicely, luckily, a pipeline that is now calculating here the amount of roots and derives us the root volume fractions automatically. That makes life much more easier. So let's get started again, just to look at changes in the soil type, because as before mentioned, we have 2 different soil types, and that's what we also clearly see in terms of the permittivity distributions at the same time of the measurement. So you see here for the upper terrace soil water content distribution, it's basically way lower than from the lower side. So here we go up till 25 in permittivity. And here we just go till 12, which is then also related to the higher and lower porosity values. And we see also lateral and vertical changes along our tubes. So this is basically measured between always two tubes, and then we get these kind of slices. So we see many variations along the tubes and also deeper down. So we also see here for the lower side that there's way more water content in the lower parts and in the upper part. And we had a clear distinction between our very top soil until 30 centimeters, which is also related to the plowing horizon. So, and then what we also looked was, okay, we had different plant types, and this were already directly seen in the data that they look differently. So when we had wheat, for example, we saw that our waves along the tubes were kind of homogeneous arriving. So you always saw an up and down over the season, but you didn't see any relation really to like where are the wheat plants. Which is in contrast to the maize. We really saw here up and downs in our signals that we could link to the location of the maize locations. And this is also visible when we look at our 3D plots of the water content over time. So along the distance, and you see here, for example, for the wheat, it's kind of very homogeneous distribution of the water content. This is a very dry day. And in contrast, for the maize, we see, for example, very clear patches that are really linked to the location of the maize. And when we saw this gave us really the hope and said, okay, here's some music in that we can use to link our GPR data to the presence of root systems. And this is exactly the work that Lena then started working on in the beginning in phase 1 of PhenoRob, when she was then trying to use this data and get more understanding about how we can really link these things together. The problem was a bit when we were just looking here at the data also related to the maize, we see here patches. In some days you see them better, and some you don't see them that greatly, because they are also affected by dynamic changes like precipitation and also about the structures that we already have in the soil. So therefore, Lena came up with a so-called trend-corrected spatial permittivity deviation, where she removed static and dynamic changes over time. And when she was doing this, she could then really see what happens in terms over time. So you see here different measurement days over the season, and for exemplary place here for all the different depths that we have the tubes. And we see that over the season, from blue to reddish, we see that the variability of our signals is actually increasing. Sometimes they go down, sometimes they go up in terms of the changes in permittivity. And when we now have a look here in contrast and compare it to the root length densities in the same tube, but keep in mind that's a mean averaged value for the entire tube. And here we have information spatially along the tube, but we still also see a similar effect. So we see over the season, we have an increase in root length density that is nicely linked here with our changes in variability in the permittivity. And that's why Lena then in the next step, we're cross-correlating the standard deviation of the probability density functions, so actually the variability that we can see with the permittivities, with the root volume fractions. And what she found was that for half of the data that she had, she actually found a pretty okayish correlation, so more than 0.5. Half of the data were not that great in the correlation, but there are also some ideas why. So for example, not that much data points. But in the end, what we could say is that we actually have a pretty good indicator that our variability changes and the permittivity is also changing with the presence of the roots. So it goes up and down depending on how much roots we actually have. So there seems to be a clear link here that we also now in future studies wants to further investigate. Because one problem was that we had here that we had some limited data in terms of spatial, but also temporal. And this is something that we last year tried to resolve by having way more data. So just as a very small glance of what currently is taking place in the rhizotrons, because we had the opportunity to buy a new system, which allows us getting higher resolution images, so 500 megahertz. And this time we also applied different nitrate applications. So here in the upper part, we have more nitrate applied than here, but all still in a range which is practical used in agriculture. Just to give you already some idea about how the signals are changing. So this is a typical 200 megahertz data set, and this is a 500. And you see already here with the 500, we can better already see here these patches, but we also see here a change in the amplitude. And this is exactly what I mentioned before. The ion concentration with more nitrate is attenuating our waves. And this is already here kind of hopefully visible for us to see, that we can see already here a change in the nitrate applications. And when we look at the 3D images, we also see for the 500 megahertz already here more patches popping up. They are better distinguishable in terms of the dimension, and we see already more soil structure heterogeneities. And this is currently the work that Sophia Schiebel is doing. And in future, we hopefully see way more of these results, and also linking the correlation new camera system that gives us more route information along the tubes. And to just sum up, yeah, I hope I convinced you that GPR is also a quite nice tool to not just characterize soil variables, that we also can see water content changes over time at different scales, that also at the surface applications, this multi-channel device is very suitable actually to be applied. But of course, to have other data sets like ERT and EMI is always good to have, because it always gives more information and they are nicely complementary to be applied in the field. And especially on the rhizotrons, we have seen that there is a clear link between the root volume fraction of the plants in relation to the variability of the permittivities that we can see. And future work is, as it shows here in the two images, is that we want to use a kind of a digital twin of our rhizotrons to really see, okay, what can we resolve, what also in terms of inversion, even more structures can be possibly got out of the data, and how also the acquisition is then good to be optimized, because it's all a matter of acquisition time, what we can do there. And then also here, that's a nice image of one of the tests that we already did in Klein-Altendorf, that we also really want to bring this now to the field to see what we can do. Of course, such kind of measurements is not possible in the wheat application, but like for corn, you see this is kind of some ideas how we could do it in future as well, to see also the changes over time, even when the plants are growing. So yeah, so this brings me to my end. And again, I just want to acknowledge all the funding agencies. So it's of course FINEROP, but also soil-free part of the work was shown. And this is just giving you a nice idea about how we can combine EMI and GPR really on the field scale.